Welcome to Lesson 5, Complex Functions. In this lesson, I'll talk about complex functions and their graphs. On this slide, we define a complex function. It's simply a mapping from the complex numbers into the complex numbers. We have an example here, f of z equals z squared. We take a particular number like 1 plus I, we square it, and we get, after some algebra, we get 2i. So the function f of z equals z squared maps 1 plus I into 2i. And of course, it maps every number in the complex plane to another number in the complex plane. The set from which you're mapping, which is a subset of the complex numbers, is called the domain. Then if you look at all the mappings too, in other words, all the f of z's, and you accumulate all those, that's called the range or the codomain. And that's also a subset of the complex numbers. So our example here, we map from the entire set of complex numbers to the entire set of complex numbers, but it doesn't have to be the entire set. We can work with subsets in some cases. Yeah, just one word of warning, which I'll bring up later, but the word domain is used two different ways. When talking about functions, it's used as we've described here, but you also have in the area of topology, which will come up later, a domain is an open connected set. And that condition is needed for a number of the complex theorems that we'll see a little bit later. I'll bring it up again, but just to caution that there's potentially some confusion on this point. Complex functions could either be single-valued or multi-valued. Single-valued function is pretty much what you would think. You put in one value for z in the function and you only get one value out. Multi-valued function, you put in one value for z and you can get one or more, or should I say two or more values. So we've seen this already. When you have the nth root of z, there's n values for each input. Take a simple example of that, z square root of z, and you take f of minus 1, then you get the square root of minus 1, which is either plus or minus I, so you get two values there. A multi-valued function can be seen as a collection of single-valued functions where each branch has just a single value, and we can typically pick a principal branch and work from there. And we'll see some more of this when we get to logs and the exponential function in future lessons. The real and imaginary parts of a complex function can be mapped separately. And we start by just looking at z equals x plus iy and seeing how that gets mapped. A single point, it gets mapped to some u plus iv in the codomain. Now if we do that for every value of z, as represented by x plus iy, then what we get is f of z equals a real part, a function u of xy, and then I times another real valued function v of xy. A little bit easier to see if we do an example, but first let me point out you can do the same thing with polar coordinates. You can break the function f of z into a real and imaginary part where the real part is a function of the modulus and the argument, and the imaginary part is also a function of the modulus and the argument. So taking an example here, f of z equals z cubed, you plug in x plus iy, you cube it, you get this expression here. You can collect the x cubed minus 3xy squared. That's basically your u of xy. Then you collect the imaginary terms, 3x squared y minus y cubed. That's your v of xy. And you can do the same thing for the polar coordinates. You put in r e to the I theta for z, cube it, use Euler's formula to get this expression. Then you take the real part the r cubed cosine 3 theta, that's your u of r theta, and then your imaginary part is r cubed sine 3 theta, and that's your v of r theta. Okay, plotting complex functions. There's a basic issue here that we're mapping from a two-dimensional space, the domain, to another two-dimensional space, the codomain. And we can only visualize up to 3 dimensions, and so there's some techniques required in order to get at least a partial view of how things look in terms of plotting a complex function. One technique is to just plot part at a time. So we might take a horizontal line in the domain and see what that looks like in the codomain, or take a vertical line, or maybe even just a sloped line in the domain and see what that looks like in the codomain. And then you put those together and you get a bit of a view of how things look. So in the next couple of slides, we'll actually employ that technique. In this slide, we consider the function f of z equals z squared. And we want to do a mapping of the y equals c, which is a horizontal line. We'll see what that looks like. It turns out to be a parabola. But first we need to expand z squared in terms of x and y, which I've done here. You plug in y equals c, we get this here. Then we let u equal x squared minus c squared, and v equals 2cx. So u is the real part in the codomain, and v is the imaginary part in the codomain. We solve for x in terms of v in this latter equation. We get x equals v divided by 2c. We plug that into this equation for u, and we get u equals v over 2c squared minus c squared. And that's a parabola opening to the right in the codomain. If c equals 0, then you just get u equals x squared and v equals 0. So uv is equal to x squared comma 0, which is basically the positive real axis. Continuing with our mapping of f of z equals z squared, we're gonna map now vertical lines. So we let x equal c. We plug that into our equation from the previous slide. We get the equation shown here. We let u equal this part, the first part here, the real part, and then we let v equal the imaginary part. We solve for y in terms of v in this equation here. This all looks pretty similar to what we've done in the previous slide. We get y equals v over 2c. Plug that into the equation for u. And we get u equals c squared minus v squared over 2c. So we again get a parabola, except it's the minus sign makes it point to the left. And if we have c equals 0, we're going to get a horizontal ray and pointing to the left. It's basically the negative real axis. In this figure, we have a depiction of the equations that we derived in the last several slides. The red horizontal lines are what we mapped initially, and as you can see here, once they're mapped, this side is the domain, this is the codomain. Once they're mapped, you can see they're mapped to parabolas pointing to the left, to the right, excuse me. And then the vertical lines in blue are mapped to parabolas pointing to the left. And I did this using Wolfram Alpha. I have a subscription, so I'm not sure if you don't have a subscription, if it'll give you this much. But you might want to give it a try. Try putting in z cubed. You'll see it. You get an even more complicated diagram to read. But they do the basic For any complex function you plug in, they'll take a grid of vertical and horizontal lines, and then you get a mapping of how they look in the codomain, or at least that's what Wolfram Alpha does. There are other free applications on the web, and you may want to look some of those up. I use one in a subsequent slide I'll mention in a minute. Another approach in terms of plotting is to look at translations, rotations, and reflections. In the first example, we have a translation, f of z equals z plus 1 plus I. This takes each point z and maps it in the codomain 1 unit up and 1 unit to the right. We have rotations and expansions. In this case, if you have f of z equals z cubed, then the rotation comes from the polar coordinates. You can see you have an angle here, an argument of theta, but here it's 3 theta, so you've multiplied the angle by 3. And of course, the radius or modulus gets bigger. If you're greater than 1, it's less than 1, then you're shrinking down the mapping. Reflections are also possible. F of z equals the conjugate of z maps everything in the upper half plane to the lower half plane and vice versa. And finally, you can combine these different translations and rotations. And here we have f of z equals z minus 3i cubed. So first we translate, we move down 3 units, and then we do a rotation as described above. Here was the z cubed. Well, in this slide, I'm graphing several vertical and horizontal lines related to the function f of z equals z cubed. You see here the red line gets mapped in the codomain to this nice curved figure. If you go about the same distance below the real axis, the green line gets mapped to a very similar shape, but it's pointing in the opposite direction. We can do a vertical line, and you get the same type of figure, but it's pointing to the left. I didn't do one in the negative area, but if we did a negative line here, you can imagine you're going to get the same looping structure pointing to the right. These are all less than 1. If you take something bigger than 1 or outside of 1 or minus 1, like here with the blue, you also get a loop. It's just that it's bigger than what can be shown here. You can imagine this is coming towards to the right, and this is going towards the left, and they cross, but it's well below what I have in the chart. So I use the online application listed up here at the top. In addition to letting you do straight lines, this application lets you do, I believe, circles, and you can also do individual points and some freehand drawings and get a sense of what the mapping looks like. So you may want to give that a try. It is free of charge.